Okay.
Okay.
All right. So good morning, everyone. Welcome to the oral exam of Khai Xiang. And so we will first let Khai Xiang give a presentation for 30 to 45 minutes, and then we will have up to 15 minutes for Q&A, and then we will do closed door session. Yeah. So Khai Xiang, please.
Okay. Thank you, everyone, for taking the time to be here on a Monday morning. And I'm happy to share with you what I've been up to the past few years and to describe my work titled Hamiltonian Monte Carlo variants.
Sorry, can you hear you? Yeah.
Oh,
I cannot see your video. Yeah. Okay. Now it's okay. Yeah.
Okay. Yeah. Okay. So I would first like to mention my supervisors, Professor Alexandra Thiery from NUS Stats Department, as well as Dr. Matthew Graham from UCL. Yeah, without their help and support, I wouldn't be here today. Okay. So my talk is basically broken down into 4 sections. I'll give you some preliminaries into the basics of Hamiltonian Monte Carlo, or HMC, and I'll describe the 3 projects that I've did over the course of my PhD, which is manifold lifting for Gaussian models, an extension of that idea for general models, as well as a reflected version of the Hamiltonian Monte Carlo. So just to give a very brief overview, the main question, or the golden standard that we're trying to answer, is that given observations Y, we want to infer parameters theta of a statistical model. So we come across such questions in, for example, physics. If we are given some temperature measurements at these points Y, or these red points, can we work backwards and infer the entire conductivity of this piece of material here? So another way to, another time we might see this is if we have maybe some stock prices or option prices, and we are assuming a stochastic volatility model, then we might ask, what is the volatility that leads to the prices that we observe? And lastly, if we try to understand some neuronal dynamics, we might interpret it as a circuit, and then we're trying to ask questions like, given some current signal or voltage signals, what are the neuron properties and what are the dynamics properties? So this area is generally also called uncertainty quantification, inverse problems, Bayesian inverse problems, or parameter estimations. So a Bayesian treatment towards this problem is to consider the posterior density, which is made of the likelihood and the prior. And we are considering just a proportional density to these 2 terms. And what it comes down to essentially is the ability to take posterior expectations with respect to some function. Here we say phi. And typically this is intractable because it is really high dimensional, and any numerical schemes is impractical to run. So the way we tackle this, there are several directions to go about it. But one of the ways is to sample, which means to say that we generate a Markov chain. So theta samples distributed according to the posterior, and then we compute a Monte Carlo approximation, which is basically just an average. So the way we generate these samples is paramount, and we want to generate them so that this estimate over here can converge really, really quickly. So to describe HMC, we are going to define the position of a physical system here with our inference variable called theta. We will have a fictitious momentum variable called P. And then we're going to have the joint distribution of the 2 called theta tilde here. And then here we define this thing called the Hamiltonian function, which composes of the potential energy and the kinetic energy. So one HMC iteration goes as such. We first draw a momentum from a normal distribution according to some covariance mass matrix, which is something that we pick. So after picking this momentum, then we integrate this system, this Hamiltonian system over here for a certain amount of time. And lastly, wherever we land, we will choose to either accept or reject it with some probability described here. So to quickly just give a picture. Okay, wait. So one last thing is, of course, in real life, this dynamic that we observe here, this is continuous, and then we can't really solve it perfectly. So in real life, we approximate it numerically using a symplectic integrator, such as the leapfrog integrator. And this leapfrog integrator comes with 2 parameters, which is the number of leapfrog stacks L and the step size itself, which is the discretization parameter, epsilon. So here is the typical picture. So the momentum P essentially chooses the Hamiltonian that we're at, which means this red loop that you see, this is the predetermined trajectory once you pick the momentum. And the idea is that we want to move along this trajectory. So if we can stay along this red line, that'll be perfect. But in real life, we are using the black approximation. So we're doing this kind of jagged steps, sort of. And then we approximate it using a number of steps. So in this case, you can see one step is roughly this wide. So this is the step size, and we're taking 5 steps in this case. And wherever we land, we are trying to compute if we accept it. And that's roughly corresponds to how close we stay to the orbit. If we stay on it perfectly, we always accept. If we're really far from it, there's a high chance to reject. So that's the basic of HMC. And I think that's all we need to be able to understand moving on the basis of my work. So here we consider, first of all, an additive Gaussian noise model. So what that means is that we have the inference variable theta. We act upon it with a forward operator, F, and then we corrupt it with some noise, which is this eta variable. And then with some noise intensity denoted as sigma. So the observation here is that as the noise intensity goes low, goes to 0, the posterior mass concentrates around a manifold. So as the noise vanishes, you are just left with y equals f theta. And this defines a manifold when f, the operator, is non-identifiable. So what that means is that we have equivalent solutions that is indistinguishable, statistically speaking. So I think the best way to illustrate this is through an example. So here we consider a forward function that looks like this. And then we consider a constant noise with one observation here. Okay. So in this case, then the posterior reads quite straightforwardly with the Gaussian prior and a Gaussian likelihood. And we see that when we decrease this noise over here, when this noise goes to 0, the mass of the posterior concentrates around this kind of loop shape, tightens around it. So that's the main observation. And it's a problem because if you're considering moving along this, this posterior, we can only take really small steps. Otherwise, we might jump out or, and then end up in regions where we suffer from a lot of rejections. So here we illustrate that standard MCMC methods are forced to take a small step size that is proportional to the noise intensity. And here we are looking at the acceptance rate on average. So what all these, for example, these top 5 here, what they say is that as the noise scale gets lower and lower, the step size also gets lower and lower in order to maintain some constant acceptance rate. Which means to say the smaller the noise, the smaller step size, and that decreases the efficiency of the sampler. So the goal is to design an MCMC method that is robust to a decreasing noise. And spoiler alert, this is the method that we use, and it is able to stay robust. As noise goes down, we are able to achieve a high acceptance even when the step size is relatively large. So to define the method, we begin by lifting the posterior, or we call it lifting the posterior. So we first consider the constraint defined by the model, which is simply just taking the y, move it to the other side. We have this constraint function. And using this constraint function, we can define an extended posterior with the co-area formula, where these are the joint priors of the variable theta and eta. And here we have this kind of change of variable correction term that is called the gram matrix. So this is the log determinant of the gram matrix that is computed using the Jacobian of the constraint. And this density is supported on a manifold defined by fulfilling the constraint. So when we fulfill the constraint, which means when the data agrees with our model here, we have a manifold structure. So one important point to take note is that the original posterior pi is in fact the theta marginal of pi bar. So this allows us to sample jointly pi and eta, and then simply discard the eta components if we want to recover just the pi, just the theta component that is distributed as pi. So to show some pictures, so this is what the manifold looks like at the end on the toy problem. You can see that as noise goes smaller and smaller, the posterior that tightens on the latent space remains diffuse on the extended space here. Which means to say that now if we try to move around it, we can take large step sizes. And of course, now and then it moves to a question of if we can actually achieve that in practice, and we can, in fact, using the constrained HMC algorithm. So for now, I will not go into the details of it. Safe to say that constrained HMC is basically HMC with additional projection steps that are necessary so that the sampler stays on the manifold. If it turns out that we have extra time, which is a little unlikely, then we can go into a bit of the details. Okay, but the main idea is that instead of sampling a very constrained, very tightly concentrated posterior on the latent space, now we are adding dimensions to the problem so that the posterior that is on the extended space is diffuse. And it doesn't live in the entire space, it lives on a manifold in that extended space. Therefore, we must be able to sample on the manifold. And the claim is that we can do so efficiently even as noise vanishes. So let's see if that's actually true. We will demonstrate a bit of numerical results. So here we demonstrate two sets of results where we are observing the robust performance of our method, as shown that as noise decreased, the efficiency does not drop. These are across the different, different inference parameters, whereas standard HMC falls as such. So all these efficiencies measures, by the way, are normalized by computational time. So that's an important point because the constraint algorithm, albeit quite powerful, it is rather expensive to run. So we must normalize by the computational time to be fair to simpler methods. And here we are also running the Riemannian manifold HMC, and that fails as well. And for another model, in this case, we are looking at the state space model, we're seeing a similar picture, such that the HMC methods fail as noise vanishes, whereas our method is largely robust. And here, in fact, we see that as noise vanishes, HMC methods are starting to fail to converge altogether. So this is described by a large R hat value. Okay. So that roughly describes the first work, where we are essentially claiming that we observe that HMC breaks down in the vanishing noise regime. And our solution to that is to, instead of sampling the latent posterior, we are sampling an extended posterior that lives on a manifold. And the contribution is that on this posterior, the extended posterior, it remains diffuse even in the vanishing noise regime, and we're able to sample it using the constrained HMC method. And the cost of sampling here is the minimum of the dimensions of the inference variable times the quadratic of the noise variable, or the other way around, which means to say we are always quadratic in the smaller dimension and linear in the larger dimension. So in fact, so you can think about it as at least cubic in the smaller dimension. So if we consider some ways to extend this research, in the constrained sampler, we are dealing with projections, and projections usually comes with some type of tolerance. So we could investigate the proper choice and the relationship between the tolerance parameters. We could also develop a proper interpretation of the mass matrix in the extended space. So far, in the latent space, if we try to abide by the posterior geometry, we might do something like a mass matrix that is different. And that gives us a clear indication of, okay, so that directs the sampling. But in this extended space on the manifold, it is not quite clear what a mass matrix mean. And in this way, we set it to identity. And like we've discussed, it would be nice if we can alleviate this linear cost scaling in dy, because this means to say that if we have a large number of data, then this method is just going to be quite expensive. And so far, we are dealing with the additive Gaussian noise case. And it would be nice as well to break out of that assumption and consider slightly more general models. And that brings us to the second work, which is
Khai?
Yes.
Yeah, okay. Now your video comes. Please turn on your video so we can see you. Yeah, thanks.
Oh, sorry. Can no one see me?
Cannot. It was always black screen.
I can see it, but then somehow I think sometimes Khai has on your somehow
Frozen,
like
right?
yes, exactly.
Yeah. Okay.
Oh, okay. Let me turn off my video and come back on.
Yeah.
Oh, because I could see myself, so I thought that.
Yeah.
Can you see me now?
It's black. How about Michael? Can you see him?
Oh, wait a
Just do
second.
black for me.
Yeah.
Because okay, maybe this is confusing because I am sharing my screen from my iPad, but my video is coming from my computer. So
Also no.
oh
Yeah.
oh, this is troubling.
Yeah.
Wait, give me 1 second.
But just now it appeared and then disappeared.
Is no one seeing me too so far? Wait, okay. Okay, let me leave the can I leave and jump
Yeah,
back
now
real
it
quick?
comes. Now it comes. Yeah, that's good. So let's
So-
continue. Yeah, now it's good. Yeah.
Okay. Oh my god.
Yeah.
2
Please go
years,
ahead. Yeah.
Haven't figured this one out.
Yeah.
Okay.
Okay. Thanks.
Okay, thank you. Thanks for reminding that. Okay.
Actually, I have a question. Do you mind if I can ask?
Go for it. Go for it. Yeah.
So can you tell me can you go back to the slide about this non-identifiable model?
So this one?
Yes. So my understanding is that the definition of this non-identifiable model is when the noise sigma goes to 0, it collapses to a submanifold, right? Is that correct?
That's correct.
I see. And I recall reading a thesis that you have some like examples about this, like some practical statistical models that have this non-identifiable or non-identifiability of the model, right? Is it?
Sorry, say that again.
So I recall reading a thesis that you have some model that have this feature of non-identifiability, right?
Yes.
Okay. So it turns out that in another area that I'm more familiar with, so you can actually imagine sigma as some kind of temperature. So it's like you're actually having temperature going to 0 instead of, which is the same as saying the noise of sigma is going to 0. So
Yeah.
it turns out that in this case, in the statistical physics literature that I'm more familiar with, this is actually what they call non-Morse function. So Morse function is when it is identifiable. So when somehow the posterior concentrate on point mass, that's what we call Morse function. So it turns out that for non-Morse function, you're actually exactly studying that case. So it actually collapses to a manifold. So it's just more like a comment, because I find this to be pretty interesting because I do a lot more stochastic optimization, and it's similar to.
Sorry, Michael. So if it's not a short question, maybe we post
I would
session for this discussion. Yeah. So sorry for that. Yeah.
Okay. Yeah, I guess we can talk more about it later. Okay. 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 All right. So I'll carry on. So having done the first project, we extended the work, my supervisor and I. We considered more general models. And first, we remind ourselves that what are some issues with the previous method of manifold lifting is that, first of all, we are considering a Gaussian noise model, which means that we are assuming that an explicit noise term eta exists. But in many other statistical models, that's not the case. So for example, when we consider Poisson counts, such as the number of goals in the World Cup finals. Oops, I don't know why this is supposed to be larger than 0. Yeah, so in that case, we can say that the random variable is distributed according to the Poisson distribution, but there would be no way to specify a noise term like eta. Another example is classification labels. So in this case, if we consider a binary classification, so the randomness comes from the Bernoulli distribution, but it's the same thing where we can't say that there's an explicit noise term. So in this case, where would the manifold lifting methodology fit in? And of course, we're still a little bit bothered by the fact that there's linear growth in the number of data, which is unfriendly in today's day and age where there's a lot of data. So we are looking to extend the method to solve some of these problems and make it more general. So once again, we consider an example here. All right, here. So we are letting go of the assumption of a Gaussian noise model, and we're looking at a more generic probability distribution here. And the posterior, if we just expand it out a little bit, we use this shorthand called L, which essentially describes one term of the negative log likelihood. And there's a reason that this will be used later. So in this case, we realize a similar occurrence when the number of data tends to infinity or becomes really, really large, that the posterior concentrates around a set that is essentially saying that the inference variable theta is going to close in on the maximum a posteriori, which when there's a lot of data, is going to converge towards the maximum likelihood estimate. So using the same forward function to induce the same non-identifiable structure, we simulate some data, some Poisson data, and what we get is the same thing, or rather a very similar picture, such that as the number of data increases, the posterior mass concentrates around the same manifold defined by this loop over here. So previously we have vanishing noise, now we have an increasing number of data. And intuitively, they kind of make sense because when there's less noise, there's less uncertainty. And then when there's a lot of data, there's also less uncertainty. And we can see that this is further supported by the fact that when we run a lot of chains to generate this picture, we see that once again, the number of observations become large, the step size required becomes smaller. And here, our method remains robust as we are able to take large step sizes and remain efficient and maintain an acceptance rate. So now we are going to discuss how we lift the posterior without using any noise terms. So the key here is to consider likelihood computations instead. So if we assume that we have some type of auxiliary variable that is Gaussian distributed, and then we can consider the joint prior on the variable theta and the new variable xi. And we can see that these would be the terms of the density. And here we say that the posterior, we can recover the posterior if the following holds, which is to say that the density of the posterior, density of the prior on xi is equals to the negative log likelihood of given of the data. Sorry, there's a little typo here. This is supposed to be J. Okay. And here we are free to choose the auxiliary dimension and as well as a set of constraint functions that imply this function over here. So you can see that all we need is to satisfy this general constraint such that the sum on the left is equal to a sum on the right. And there's a number of ways to implement this. So to walk through the idea, we consider just one auxiliary variable. So in this case, the general constraint specializes into this form over here. And then we can simply rewrite this as a constraint function over here. So this is just some basic algebraic manipulation. And then this implicitly defines a manifold when we satisfy the constraint. So once we have this form of a constraint and a manifold, then actually we can kind of use the same idea of the covariance formula to define a density and extended density on the Hausdorff measure. Simple enough, right? So we can just do something like this. But before we move on, we have to say that in this case, the one-dimensional auxiliary variable version does not work because the extended posterior is not diffuse. So we illustrate here why. So first we start with the picture on the top. We see that you can see the shadow on the bottom shows that the density is concentrating in the latent space. But we also notice that the same thing has happened in the extended space. Moreover, the density here is going to be focused on the valley of this manifold. And the valley, there's this valley shape is because of the Gaussian assumption on the auxiliary variable. So essentially, which means to say that if we look at here, there's this valley over here. And then a lot of the mass is concentrated near here. Now, this is difficult to sample because we are at this valley shape, and there's going to be a lot of convergence error when we're trying to stay on the manifold, given the rather high curvature compared to someplace else, let's say here. This is more or less kind of flat-ish. So using one-dimensional auxiliary variable does not allow us to escape the concentrated posterior, and we see that indeed, even as we use the constraint HMC in this method, it deteriorates as the number of observations becomes larger. So, okay, so the next natural idea is to try two-dimensional variables. And so the formulation is rather similar in that we consider two constraint functions in the same form, with the main difference that they are computed on different subsets of the data. So here we consider a partition of the data into two subsets, and then we assign one to each constraint function. So correspondingly, this gives us two manifolds. And we note that if we satisfy both constraints, then this jointly satisfy the general constraint over here. And similarly, what we can do is simply to write it in the traditional form that we introduced, which is to vectorize this so that we can consider this constraint function of two outputs, and then similarly define an extended posterior on the manifold using the covariance formula, this time with this form, which is the kind of the squared. Here is kind of, this is the square norm of the auxiliary variable, and then we have a gram matrix that is 2 by 2. And to sample, simple enough, we just define, as in HMC tradition, the position to be the joint variable theta and psi, and then we can just sample using constraint HMC. So we applied this to several models. Oh, wait, sorry. Yes, so prior to this, I have not described in detail how we want to choose this partitioning and how we're choosing a partition that actually solve the problem of the 1D case, which we call the valley problem. So the idea is that if we have a valley and then a lot of density here, what we want to do is to define two manifolds that look something like this, so that for each of the manifold, the concentration of the mass is away from this valley and away from this valley. So instead, they just concentrate around here, maybe, and here. And in these two regions, it is much easier to sample. So that's the main idea, at least. All right. So again, so based on the intuition that we want to skew the values away from the bulk. So for ordered data, which means that we can just kind of compare them large to small, we recommend to use simply the median. So anything that is above the median, we assign to one set. Anything that is below the median, we assign to another set. You could also use something like mean. It's a similar idea. And for categorical data, we simply just group the data sets by class. So if you have binary classes, then we have 2 partitions. If we have 3 classes, then we recommend using 3. The idea is that if we assign the constraint function to abide by one subset of data, it is going to give us a different solution than looking at the whole data set. So each constraint function should be sufficiently biased. And here we can see the results. Given our formulation of 2D auxiliary variables, what we can see is that upon lifting the posterior onto the extended space, this posterior here is now diffuse. You can see that the concentration effect still kind of occurs, but because of how fast this manifold rises on the sides, the density is actually kind of, instead of being here, it is now smeared all over here. So this makes it diffuse, or at least much more diffuse than it would have been in the lane space. And to verify this, we can check a few examples. So for experiments, we just run it on a torus manifold, right, to make sure that it is able to identify any obvious errors if it works or don't. So we are here, oops, yeah. Based on the same Poisson model, where we just assume Poisson count data, we see that the method that we have works quite well here, whereas the standard HMC method deteriorate as the number of observations becomes larger. And they also suffer from convergence problems as we have more and more data. So this shows some support towards the robustness of the method that we propose. In another model, the Bernoulli model, which is a binary classification problem, we see that we can kind of see the same thing where the ESS, the efficiency stays the same, whereas the HMC efficiency kind of drops down. We have something a bit of a kink here because of convergence issues, so this point is kind of discounted in a way. However, when we normalize by the compute time, here we see a slightly different picture where the constrained version, the HMC version drops at a rate, whereas the constrained version drops at also another rate. And past this point, the constrained version does better. And this is because as the number of observation increase, the compute time increases as well for the density, for the likelihood of the Bernoulli model. So any method that you use is going to take longer time just because there's more things to compute. And for example, if you go back, this does not happen to the Poisson model because the way the densities work out, you can pre-compute these terms as a scalar. You can just sum them up, and then so you can kind of treat them as constant with respect to n. Lastly, we consider a Gaussian model, and the same picture, so this is the same picture that we see, which is that our method is going to be robust, and whereas standard HMC is going to fail and suffer from some convergence issues. And similarly, we can pre-compute some of the items so that even though the number of data increases, the runtime for functions are going to be constant with respect to n. So that about wraps up the second project. To give a short summary, here we are focusing on the breakdown of MCMC as we have larger data. To lift the posterior without noise, we are using auxiliary variables based on likelihood computations and a splitting of the data sets. With the lifted posterior, the constrained HMC is able to remain efficient in the large data regime. And importantly, we contribute towards reducing the cost because now, instead of having dy, we have d psi here, and we are free to choose this. So of course, this affects the overall efficiency, but in our case, this would just be 2. And last but not least, the method is compatible with general probabilistic models that is beyond the Gaussian noise cases. To further develop this idea, we can consider more principled ways to partition the observations. And also we can in-depth explore the optimal choice of number of auxiliary variables. And lastly, we are assuming that the auxiliary variable is distributed as normal, and that need not be the case, even though in our experiments we've tested several choices and this works the best. It could do with more theoretical and numerical corroboration. All right, so now we are moving on to the final project, which is the reflected Hamiltonian Monte Carlo. So this project is distinct from the previous two. It's not a continuation, and we look at a slightly different, a completely different problem. We start off by noticing that HMC is quite sensitive to the number of leapfrog step parameters. Among all the parameters, it would be the one that is kind of least studied and least understood. So once again, we bring back the picture of the HMC here. We see that we are taking steps. And moving around this figure 8 over here. And if we take too many steps, naturally we see that we are going to go back to where we were, right? We're going to just make our way back, and then we can take many, many loops, and then it wouldn't be very useful in terms of exploring the state space. However, if L is too small, then we are also suffering from poor explorations, and then it's going to lead to low sampling efficiency. So picking something in the middle in the sweet spot is not trivial. So far, the best method that we have, or the most popular method, is the NUTS method, which is the no-Newton sampler. So the no-Newton sampler dynamically tunes the number of leapfrog steps such that it will continue to take leapfrog integration steps until it detects a U-turn back towards the starting point. So as long as the next step does not increase the distance between your starting point, that is when you terminate the trajectory. So it's very nice and easy to use, but the bad thing is that it is rather expensive to run if you start to count the compute. And it is not so trivial to run on parallel architecture as well. So our goal is to design a method that achieves long trajectories without having to tune the number of leapfrog step L. So we are inspired by the bouncy particle sampler here, and we consider a kind of HMC version of it with a delayed rejection step. So we walk through the steps of the reflected HMC. So the first step, starting from here, we propose the blue arrow here. We propose this new state, and we accept it with some probability. So this is just a standard kind of metropolis Hastings step. Next, if we reject it, we propose again. This time we propose a reflection. So from here, reflect towards here. And what we get is this green arrow over here. And we accept that with some probability. And this derivation can be found in the delayed rejection literature. And lastly, if we reject the delayed rejection reflection as well, then we are forced to take a backtrack, which means to say we are going to stay where we are and our momentum is going to be negated. So this is bad because it would mean that we might come a long way from somewhere, and then upon a rejection, then we're going to head back, which means to say in terms of exploring the state space, it's not going to be very beneficial. So in between this moment, reflected Hamiltonian dynamics, we are going to update our momentum partially. We consider two ways to do so. So first, we have the full refreshment, which is to say that with a coin flip, essentially, that the momentum is going to refresh according to this probability, and it's going to refresh fully just as in standard HMC. So what this means is that it's going to keep on moving, integrating, and once a while, it's going to change momentum. So it gives us the effect of a variable leapfrog trajectory. And then we also have the autoregressive refreshment, which considers a continuous way of modifying the momentum. And all these are going to be governed by this parameter here called kappa, which is the update rate. And here, the larger the kappa, the more aggressive or more frequent the momentum updates. And the goal is to tune kappa instead of L. So just to get a feel of what kappa does, we look at some of the results, and this is simply efficiency on the y-axis over a range of kappa values. We see that for all the cases, there's going to be some sweet spot where we get the best performances. And then if it's too high, it's going to deteriorate into a Mala-like performance. And if it's too low, which means to say that we are not modifying our momentum enough, and that means that we're going to be stuck on the same Hamiltonian level set, and that's going to result in a random walk behavior in that sense. So as in most MCMC tuning parameters, too big is no good, too small is no good. Somewhere in the sweet spot in the middle is what we want. And given this momentum update, on average, we can say that reflected HMC takes about 1/k leapfrog steps, 1 kappa leapfrog steps. So the way we tune kappa is quite straightforward. We start by running in parallel a lot of chains, a lot of short chains using different kappa. And then for each of the chain, we record the first lag where the autocorrelation falls below a threshold that is predefined. And using that first lag, we approximate the rate of decay of the short chain autocorrelation. So this approximation is just a very basic truncation of a power series of a exponential function. And lastly, from this approximation of the decay, we just pick the kappa value that gives us the faster decay, right? So let's see how the method does. We tested this method on somewhere around, I don't know, like 15, 20 examples, which includes stochastic model, stochastic volatility models, item response models, logistic regression, as well as neural network classifications. So first and foremost, we are interested to see if the reflection does any good at all. And here we are comparing the methods that we have over methods that have no reflection. Here we call it the GHMC, which stands for the general HMC. So these are just the same methods with the partial momentum updates, but without the reflections. And in this case, we roughly see that if we just look at the median, for example, that the method that we have outperforms the methods without reflection by something about 30%. Of course, these are estimates, but it's roughly around there. And if you like, you can consider the errors as well. So it's safe to say that the reflection gives us some benefits in terms of an increased acceptance rate. And next, we're considering the tuning of the method, the efficiency of, oh, sorry, what am I talking about? The performance of the simple tuning that we propose, in that if we tune it on a grid search, which means to say we are just running all the chains and picking the best, we see that the proposed tuning method gives us about 70–80% of the performance, of the optimal performance, which is to say that with just some very cost estimation, we can get about 80% of the way there. And lastly, we are considering the reflected HMC against baselines such as nuts and a well-tuned optimal HMC here. And we see that the optimal reflected HMC performs more or less the same as optimal HMC. You can see it's roughly 1. So these are averaged across all, like something like 20 experiments. And the practical HMC, which is basically reflected HMC tuned with the tuning method proposed, performs better than nuts by about 30–60% over here. So this is because, again, nuts is rather expensive. Whenever it takes a step size L, it roughly runs 2L, twice worth of the computation necessary to make sure that it works well. So in a nutshell, the reflected HMC is composed of 2 kernels, a reflected Hamiltonian dynamic kernel, as well as a partial momentum refresh. And the reflections improve the acceptance rates, while the momentum updates govern efficiency through the update rate. We tune the update rate using a rough estimation of the chain correlations. And then we see from our experiments that reflected HMC outperforms nuts by something like 30–60%. And upon is not to be missed is that the reflected HMC can be run in parallel quite easily through vectorization, and which is what we have done in our experiments as well. So in the to take this further, we can consider more theoretical approach to tune the update rate, and more sophisticated heuristic perhaps, as well as a detailed comparison between the two momentum refreshment rates, refreshment schemes, which is the autoregressive and the full. So in our experiments, we see that the autoregressive method works better than the full refreshment by a little bit. But yeah, so this is also an arena worth investigating. All right, so that wraps up everything I've done in the past 4+ years, and thank you for listening.
Thank you very much, Khai. And I think it's time for us to open the discussion question, to the public. Please feel free to unmute yourself. So, only question, feedback? If not, then I will ask others to leave, and we will make a closed door oral exam, right? Examiners and also Khai need to stay, and others please to leave.